Aliens might already be out there, and the next generation of space telescopes could actually see them. Not in flying saucers or shadowy silhouettes against the stars, but in the faint, twisted glow of polarized light bouncing off an alien ocean, or in the ghostly signature of molecules that twist in only one direction, the same quirky habit that all life on Earth shares. And the key to unlocking this interstellar mystery, a telescope so advanced, so precise, it could detect life not by accident, but by design. It's called the Habitable Worlds Observatory, and it's humanity's most serious attempt yet to answer the oldest question: are we alone? At first glance, the HWO might look like just another ambitious piece of NASA's long pipeline of missions, one more telescope among many. But make no mistake, this one is different. It's not built to study galaxies or unravel black holes. Its sole purpose is to find life. Not just planets that could be habitable, but worlds that are inhabited, teeming, thriving, alien ecosystems hundreds of trillions of kilometers away. Getting there, though, is like trying to solve a cosmic crime scene. You can't just zoom in and take a picture of the alien equivalent of a rainforest. You need evidence, layers of it. And the HWO is being designed to collect that evidence with surgical precision. Its mission unfolds in 4 stages, each one peeling back a layer of the unknown. First, identify potentially habitable exoplanets. That alone is no small feat. You're looking for tiny, dim specks of light next to the blinding blaze of their parent stars. But HWO is equipped with a built-in coronagraph, a kind of cosmic sunshade that blocks the overwhelming glare of the star, letting the light from the orbiting planet shine through. Second, look for the hallmarks of life. The most immediate clue? Color. Specifically, biopigments, substances like chlorophyll that reflect and absorb light in particular ways. These signatures show up in polarized light, which vibrates in specific directions. HWO's polarimeter is designed to detect those subtle twists and turns in light, revealing whether a distant world might be cloaked in alien greenery. But even that isn't proof. So the third step is to map the planet's surface. Not in high definition, but enough to distinguish continents from oceans, clouds from deserts, and, just maybe, forests from barren rock. Variations in brightness, reflected light, and spectral fingerprints help sketch out a rough global map. Such mapping, though crude, could be the first time humanity ever sees an alien landscape. And then comes the final, breathtaking step: searching for chirality. Life on Earth exclusively uses molecules that are handed, either left-handed or right-handed, but never both. This asymmetry, called homochirality, is a universal trait of biological systems. And astonishingly, it leaves a telltale signature in circularly polarized light, a kind of light that spirals as it travels. Circular polarization is rare in nature, and its biological origins make it stand out like a flare in the darkness. If HWO detects it, we'll be able to trace the fingerprints of alien life without ever stepping foot on that distant planet. Unlike atmospheric gases that can be formed by volcanoes or other geological activity, chirality is incredibly hard to fake. But here's the real challenge: the signal would be faint. Only about 0.1% of the total spectrum, hidden among noise, distortions, and the glare of nearby stars. But HWO's instruments are being engineered to catch it, to sift the whisper of life from the cosmic static. And it's not alone in the hunt. Telescopes like JWST and upcoming ground-based observatories are already scanning the skies, identifying exoplanets that sit within the so-called habitable zones of their stars, regions where conditions might allow liquid water to exist. These discoveries provide the target list. HWO brings the forensic tools. The mission scope goes beyond mere detection. It also aims to characterize these distant environments in detail. How much of the planet is covered by water or cloud, what kind of atmosphere it has, whether there's seasonal variation. These insights would shape how we think about habitability itself. perhaps even redefining what we consider Earth-like. This isn't sci-fi fantasy. The concept is backed by real hardware plans and international support. The Astro 2020 Decadal Survey prioritized HWO as a flagship mission, recognizing its transformative potential. It's a long-term investment, a decade-spanning project that may define the course of space exploration for the rest of the century. Of course, $10 billion is a towering sum, but so is the cost of Hubble and James Webb, and no one today questions the value of those instruments, which revolutionized our view of the cosmos. HWO could be the next step in that legacy, not just expanding our knowledge, but changing our place in the universe. The implications are staggering. Discovering a planet with biosignatures would change science, religion, philosophy, everything. It would force us to rethink life itself. Are we a fluke or one instance of a cosmic pattern? And what if we find nothing? That answer, too, is monumental. If life is rare, if Earth is truly exceptional, it places a responsibility on us to preserve what we have, because it may be all there is. One way or another, HWO promises to break new ground. It's not about flashy visuals or viral headlines. It's about deep, deliberate science, about asking the hardest questions and building the tools to answer them. When that glimmer of twisted light finally reaches us, it won't just illuminate a distant planet. It will illuminate ourselves.
Imagine you're staring at the night sky, just another ordinary evening, and suddenly a star blinks. Not just once, but in two quick, identical flashes. Then silence. Nothing. For years. Until one day it happens again. Somewhere else. Another star, another double blink. No explanation. No confirmed pattern. No clear source. Welcome to the strange and captivating world of Optical SETI, where we're not just listening for alien radio transmissions, we're watching the stars, and the stars might just be blinking back. More than 6 decades ago, the search for extraterrestrial intelligence, SETI, began with a project called OSMA. Frank Drake, the man behind the Drake equation, pointed a radio dish at a couple of sun-like stars, hoping to catch a whisper from across the galaxy. Since then, scientists have tried everything: radio, infrared, microwave, even laser pulses, to answer the same old question: are we alone? And while the answer has remained elusive, it's never been boring. Fast forward to today. Richard H. Stanton, a retired NASA engineer who's worked on legendary missions like Voyager and Grace, has been quietly running his own SETI campaign from the Shea Meadow Observatory in Big Bear, California. No fancy NASA lab, no billion-dollar budget, just a 30-inch telescope, a custom-made photometer, and thousands of hours of watching the stars. Stanton isn't listening. He's watching, and not just any watching. He's sampling starlight every 100 microseconds with a technique called photon counting. The idea? If someone out there is trying to communicate with laser pulses, brief, powerful blips of light, they might be visible, even across light years. And then came May 14, 2023. While monitoring a star called HD 89389, about 100 light years away, slightly bigger and brighter than our sun, Stanton's system picked up something strange. 2 fast, closely matched pulses of light, 4.4 seconds apart. The signal didn't look like a satellite, or a meteor, or a plane. It didn't match anything he'd ever seen. The star got brighter, then dimmer, then brighter again, all within 0.2 seconds. That's not typical stellar behavior, not from an object millions of kilometers wide, and not without a very specific cause. Stanton did what any good scientist would do. He tore the signal apart, checked it against known sources of interference, atmospheric noise, birds, satellites, cosmic rays. Nothing matched. Even more bizarre, when he compared the 2 pulses, The fine structure, the tiny variations in light between the peaks, was nearly identical. It was like the star stuttered, then repeated almost the exact same stutter 4.4 seconds later. And this wasn't the first time. Back in 2019, while observing HD 217014, also known as 51 Pegasi, home to one of the first exoplanets ever discovered, Stanton had caught a similar signal, dual pulses. At the time, he dismissed it, thought it might be birds or instrument noise. But now, with HD 89389 showing similar behavior, that's at least a possible pattern. And patterns, if confirmed, can mean everything. Then in early 2025, it happened again. A third event, a new star, HD 251, 81 light-years away. 2 pulses, same structure. 3 events, 3 stars, years apart, yet all showing the same strange double blink. So what is it? Natural phenomenon? Some weird trick of light? Stanton isn't claiming it's aliens, and who could blame him? Science is full of false positives, but he's also not dismissing the anomaly, because here's the thing. Whatever caused these pulses, whatever modulated the starlight, it might not be coming from the stars at all. In fact, based on timing and structure, it could be closer, much closer, possibly even within our own solar system. Some possibilities Stanton considered include atmospheric refraction, maybe shock waves bending the starlight just right, or maybe some kind of object passed between us and the stars, diffracting the light. Could it be a satellite we haven't cataloged? An asteroid? Each explanation has problems. None fully account for what was observed. And that's the unsettling beauty of it all. We want answers. We crave explanations. But sometimes space throws a mystery in our face and whispers, "Not yet." Stanton's work is part of a growing interest in optical SETI, using light instead of radio to search for intelligent life. It's cheaper, faster, and in some ways, more precise. Projects like Laser SETI and Breakthrough Listen are also exploring this frontier, scanning the skies for patterns, flashes, anomalies. But Stanton's method stands apart. He's not sweeping the sky, he's locking on, one star at a time, watching like a hawk. And maybe, just maybe, that patience is starting to pay off. He's calling for more data, more eyes on the sky. He suggests arrays of telescopes synchronized across vast distances. If something is moving between us and the stars, these setups could reveal its speed, direction, even size. And if the star's light is being modulated without anything passing in front of it, well, that opens the door to a very different kind of question. As of now, Stanton isn't making wild claims. He's not saying it's aliens, but he's not saying it's not aliens either. And maybe that's the most honest answer we have. Because in the vast silence of space, it's the rare, unexplained pulse that reminds us someone or something might be out there, blinking, waiting, watching us back.
An invisible star, a red dwarf, hides 124 light-years away from us. And orbiting this faint celestial body is a planet that could fundamentally alter our understanding of life in the universe. Its name is K2-18b, and this is not its first time in the scientific spotlight. But now the reasons are far more compelling and perhaps historic. A team of astrophysicists from Cambridge, working with data from NASA's ultra-sensitive James Webb Space Telescope, has discovered chemical compounds in the planet's atmosphere that, on Earth, are produced exclusively by living organisms. The substances in question are dimethyl sulfide, DMS, and dimethyl disulfide, DMDS. On our planet, these gases are typically associated with marine plankton and certain bacteria. What they are doing in the skies of a distant exoplanet is still a mystery, but a mystery that might point toward extraterrestrial life. Professor Niku Madhusudan, the lead researcher on the project, calls this the most convincing evidence to date of potential life beyond Earth. If our interpretation is correct, he says, we could confirm it within a year or two. Perhaps the most astonishing part of the discovery is the quantity. The concentration of DMS found in the atmosphere of K2-18b appears to be thousands of times higher than equivalent levels on Earth. If this is not a mistake or observational artifact, we may be looking at an entire world teeming with life. But scientists, including Madhusudan's own team, urge caution. The current data, while impressive, still falls short of the rigorous standards required for a formal scientific discovery. To claim definitive proof, they need a statistical confidence level of 99.9999%, known as the 5 sigma threshold. At present, the result stands at 3 sigma, or 99.7%, a significant improvement from previous estimates of 68%, but still not enough. Other researchers and independent experts echo the cautious tone. Astronomer Catherine Hamans, for instance, emphasizes that even with reliable data, we cannot say with absolute certainty that DMS and DMDS originate from biological processes. The universe is vast and filled with exotic phenomena. We still don't fully understand what can happen inside such alien worlds. The intrigue surrounding K2-18b isn't based solely on its mysterious chemistry. The planet is roughly 2.6 times the size of Earth, and data suggests it has an atmosphere where ammonia is notably absent, a gas that should be present in a dry, oceanless world. This absence points to a compelling hypothesis: the presence of a vast subsurface ocean. And where there's water, the possibility of life follows. However, alternative scenarios remain. The ocean might consist not of water, but of magma, a revelation that would crush hopes for life. Adding complexity, the planet's very structure is under debate. Some models describe K2-18b as a mini-gas giant with no solid surface. That would render the world utterly inhospitable to life, at least any form of life we currently comprehend. Still, despite all the ifs and buts, the scientific community remains deeply intrigued. The Cambridge team is collaborating with other research institutions to investigate whether the detected molecules could be synthesized through non-biological means in laboratory settings. If such synthesis proves impossible, the case for a biological origin becomes far stronger. Professor Subir Sarkar, another member of the project, is careful with his conclusions, yet he acknowledges that the possible presence of an ocean makes K2-18b one of the most promising candidates in the quest for alien life. His message is simple and clear: watch this space. Cambridge astrophysicist Oliver Shortall, however, brings us back to reality. He reminds us that all of our knowledge about distant exoplanets is drawn from faint threads of light passing through their atmospheres. Interpreting those signals is like trying to read a smudged and half-burnt map, prone to error, to bias, to misinterpretation. Each promising signal could be either a whisper of life or a trick of the cosmic light. Yet the implications are impossible to ignore. Even the slightest probability of a biological origin for these gases elevates the conversation. This isn't just about chemistry, it's about existence. About the possibility that we may not be the only ones looking up into the void. Public curiosity has surged alongside scientific interest. News of K2-18b's chemical profile has lit up headlines, podcasts, classrooms, and conspiracy forums alike. Some hail it as our first real evidence of alien life. Others urge restraint, cautioning against the seduction of sensationalism. But in a world starved for wonder, K2-18b delivers, even if only as a promise. Further missions are already being drafted. Telescopes in space and observatories on Earth are preparing to lock their gaze on this distant enigma. New instruments, refined spectrographs, and smarter algorithms will seek to strip away more layers of the mystery. Every spectrographic fingerprint, every spectral dip in starlight brings us a little closer to confirmation, or recalibration. Science moves not with leaps of faith, but with patient, deliberate steps. And yet, some steps feel bigger than others. When we look at K2-18b, we don't just see another planet. We see a question written across the stars: are we alone? As Madhusudan puts it, decades from now, we may look back at this moment and realize it was the beginning, the dawn of a new cosmic chapter. The moment humanity first saw the glimmer of a living universe beyond the solar system. The discovery hasn't been made yet, but the journey has begun, and that alone is already extraordinary. Picture a silent ember drifting toward the sun, moving so quickly that no gravity well in our system can bind it. That ember, provisionally tagged 3I Atlas, appeared in late June when the Atlas Hazard Survey cameras in Hawaii and South Africa logged a faint, fast intruder. Initial orbital fits showed an eccentricity greater than 1, the mathematical stamp of an origin beyond the sun's reach. We have met only 2 such emissaries before, 1I Oumuamua in 2017 and 2I and Borisov in 2019. Now a third arrives, tugging at our curiosity and our instruments in equal measure. The object's present speed is almost 70 kilometers per second, enough to span New York to London in 90 seconds. Backtracing the path leads toward the constellation Lyra. Forward projection shows a swing past Mars on 3rd October 2025, a solar perihelion 20 days later at twice Earth's distance, and final escape by early 2026. Earth stays on the Sun's far side throughout, so the risk ledger reads 0. The intrigue ledger, however, is packed. Composition sits at the top of the to-do list. A comet would sprout a gaseous veil as ice evaporates, yet deep imaging has yet to reveal any coma. An asteroid would follow purely gravitational curves, yet a whisper of extra thrust may lurk in the astrometry. The James Webb Space Telescope can cut through reflected sunlight and sample the infrared glow for water, carbon monoxide, or exotic minerals. If the spectrum comes back featureless or metallic, theories multiply. Brightness fuels the puzzle. Even with a modest albedo, the observed flux implies a body several kilometers wide, far larger than Oumuamua, whose size was measured in hundreds of meters. A highly reflective hull could achieve the same luminosity with far less mass, a possibility that keeps technosignature specialists awake. Professor Avi Loeb, already known for suggesting an artificial origin for Oumuamua, is lobbying for continuous JWST tracking to test for non-gravitational acceleration. A persistent drift unaccounted for by gravity would demand explanations that push against the boundaries of conventional astrophysics. Statistics pose the second riddle. For centuries, astronomy recorded 0 interstellar passers-by. Now we count 3 in 8 years. Better sky coverage explains part of the surge, yet simulations indicate the detection rate is still high. Either the density of galactic debris is underestimated, or transient swarms are sweeping the Sun's neighborhood. The Vera C. Rubin Observatory, starting full operations next year, will clarify the odds by mapping every moving speck down to faint magnitudes every few nights. Structure forms the third unknown. Light curve monitoring can reveal whether 3I spins like a platter, a spindle, or a rubble pile loosely bound by microgravity. Oumuamua's flattened shape and unexplained kick remain controversial. A repeat would strengthen calls for new physics or new engineering. Rapid tumbling might indicate past collisions, freshly exposed ice, or even deliberate attitude control. That opportunity extends well beyond the object itself. Each interstellar visitor carries isotopic fingerprints of the chemistry that shaped alien worlds. Sampling those fingerprints, even remotely, refines models of planet formation, volatile delivery, and the migration histories of giant planets. In a decade, robotic missions may be fast enough to intercept such bodies. Today, we practice with photons. Time is tight. By September 2025, the object will vanish into solar glare. By the time it re-emerges, the outbound leg will dim below major telescope thresholds. Roughly 5 months remain for the most ambitious observations. Teams are coordinating radar pings, ultraviolet spectra, and high-cadence photometry to squeeze every bit of information from the fleeting visitor. Why should the broader public care? Because 3I Atlas is a tangible reminder that our solar system is not an island, but a crossroads. Somewhere, an unknown star flung this body into the dark, perhaps through a near miss with a giant planet, perhaps through a cataclysmic collapse of a binary pair. After wandering for millions of years, it has brushed past our doorstep, offering a message in a bottle. The galaxy is bustling, and we are part of that bustle. Whether the newcomer proves to be ice, rock, metal, or something unprecedented, its brief appearance renews a sense of frontier. Sky surveys sharpen, theories adapt, curiosity deepens. The next discovery may come sooner than anyone expects, and when it does, the groundwork laid today will allow us to read its story more clearly. For now, astronomers chase a streak of light across CCD frames, and every clear night might deliver a clue that rewrites chapters on planetary science, or adds a footnote to the search for artifacts among the stars. In either case, the sky is not done surprising us. Origin scenarios abound. Some simulations eject 3I from a nascent planetary system after a close brush with a giant planet, while others invoke a crowded stellar nursery where passing stars fling debris across interstellar lanes. Whatever the trigger, the body has drifted for perhaps tens of millions of years, carrying the isotopic signature of an alien chemistry lab. Radio arrays will also listen for narrow-band emissions, more out of thoroughness than expectation. After Oumuamua, technosignature protocols are standard. Scan, archive, move on, unless a signal repeats. Looking ahead, Rubin's legacy survey of space and time should uncover several interstellar objects every year, identified early enough to permit rapid robotic flybys. Concepts under study at multiple space agencies outline launch-on-alert missions that could sample surface dust or even return grains to Earth. Each discovery thus acts as rehearsal for the day we chase one down in person. Whether the outcome is ordinary or transformative, the chase itself pushes instruments, sharpens global teamwork, and teaches the next generation to aim beyond yesterday's limits.
Imagine simultaneously being born, growing up, and getting old somewhere out there in the universe. Sounds bizarre and unrealistic. And still, according to the block universe model of the world, that's exactly what happens with you, me, and other living beings on our planet. It's as if someone drew pictures about every moment of your life and then just piled them one on top of another, creating a giant block of all things that ever happen at any time and at any place. The future, present, and past exist at the same time and are equally real. The block has 4 dimensions. 3 of them are spatial. It's length, width, and height. There's one more, time. To make it easier, let's picture our world as a cuboid, which is basically a 3-dimensional rectangle. Its height and width represent 2 of the 3 spatial dimensions of the universe. As for the 3rd spatial dimension, we'll replace it with time. At one end of the cuboid, we'll drop the Big Bang. And at the other, there will be the end of the universe. Let it be a big crunch. Our cuboid is filled with every single event that ever happens. Even this moment, when you're watching this video, exists somewhere in the block. Now, we perceive today as the present, yesterday as the past, and tomorrow as the future. From this perspective, it seems that time passes. But in the block universe, time doesn't flow. There's no specific present moment since the notions of the past and future are relative. You see, we are always located wherever we are, which means that everyone remains in the present. But the block universe theory doesn't deny the notions of earlier than and later than. These relations remain no matter what and regardless of where anyone is located. For example, Molly the mammoth is located earlier than Marcus the tiger. This relation between Molly and Marcus will remain unchanged regardless of whether you're located later than Marcus or earlier than Molly. This way, in the block universe, now is any time you are located at. Past is any time or events that are earlier than your location, and future is any time or events that are later than your location. It sounds like in the block universe, we could travel in time since it's just another dimension. Well, it could be true, but of course, things just have to be more complicated than that. Traveling in time is way more difficult than traveling in space, but it's not impossible if you travel very, very fast. Traveling at extremely high speeds results in time dilation. We can travel into the future at a reasonable percentage of the speed of light, and to get to the past, we can use wormholes, shortcuts through space-time. But if we can travel in time in the block universe, can we change the past? Not really, because if you do, it'll create a contradiction. Keep in mind that, in this universe, the past is the same as the present or the future. What is past to you is future to someone else. And when traveling to the past, you're going to someone else's future. In the past, you'll act just like you do in the present, but you won't be changing the past. All your actions are already predetermined in the block universe. At the moment of the Big Bang, it's already clear that at one point, you'll travel to the relative past. Just like what you do tomorrow makes tomorrow the way it is and has always been, what you do in the past makes it the way it is and has always been. The events in the block universe do not change. As a time traveler, you don't suddenly appear in the past. It's always been the case that you're located in the past. And nothing a time traveler does can change anything in the block. Instead, whatever you do at any time makes that time the way it is. A single brain filled with fake memories of having existed in our universe. Once, this brain just spontaneously formed in a void. Sounds like something from science fiction. But this brain could actually be me, or you. There is an idea that such a brain is more probable than an entire universe that came about in the manner cosmologists think it did. And this phenomenon I'm talking about is known as a Boltzmann brain. Let's see. A brain is coming into existence in our vast universe right at this second. And everything in this brain is forming at this moment. The memories of its previous life, obviously fake, its origin, its ideas, and the perspective of the universe. But this brain perceives itself as real. In this case, how will it know that its memories are artificial and its existence is no more than an illusion? This is what the Boltzmann brain paradox is about. It's the result of Ludwig Boltzmann's debate with other scientists on the interpretation of entropy. According to the second law of thermodynamics, the entropy, or disorder of a system, can stay the same or increase, but it can never decrease. Have you ever seen shattered glass return to its previous state? Neither have I. But Boltzmann stated that even though the probability of the entropy of a system staying the same or increasing is high, it doesn't mean that the probability of the entropy decreasing equals zero. This chance is just so small that it can be ignored. But everything changes when we speak about some infinite system. If such a system, for example a universe, has an infinite number of particles, there must be at least one possibility that these particles create something structured. Let's take an infinitely old universe. Such a universe means an infinite number of possibilities where the entropy increases, and a tiny chance of its reduction when particles come together and form a structure instead of existing randomly. So Boltzmann took this idea of an infinitely old universe and ran with it. He claimed that at some point, all those randomly organized particles the universe contained could come together and form a structured system. Maybe this formation of a structure even led to the Big Bang. One more idea he suggested was of a local system existing in an infinitely large system. It could be a universe containing structure and life and existing in the infinite system of a dead multiverse. Such a multiverse would have no structure, which is what high entropy suggests. And since we know that in an infinite system, there can be only one possibility of entropy reduction. All other universes except one would be dead. Interestingly, Boltzmann said that we don't need an entire universe or even a galaxy to confirm the existence of structure in a dead multiverse. The only thing we need is just one intelligent observer. And what part of the body is responsible for consciousness and cognition? Right, the brain. It could be a single brain randomly existing somewhere in a high-entropy dead universe, containing memories of its entire life. Scientists had to admit the legitimacy of this paradox, and still, everyone was sure they could never be a Boltzmann brain. Everyone knew their existence was not artificial. But that's exactly what a Boltzmann brain would think. After all, it wouldn't know that its memories and existence are fake. This realization caused quite a commotion in the scientific world. People started to research the probability of one being a Boltzmann brain, and it turned out that the existence of a Boltzmann brain in an infinite universe is way higher than the probability of a human brain. Statistically, we are more likely to be Boltzmann brains than real breathing creatures. But it's too early to fall into an existential crisis. Sure, there's no way to find out whether you are a Boltzmann brain or not, but there's a catch. Do you remember that we've been talking about a Boltzmann brain in the context of a universe which has existed for an infinite amount of time? But our universe hasn't existed forever. On the other hand, what was there before the Big Bang? Nothing? Or a dead multiverse where all the particles came together and caused the Big Bang, which led to our structured universe? Sounds uncomfortably close to the description of the Boltzmann brain universe.
Since 2007, astronomers have been receiving super-strong and ultra-bright radio signals that last just a few milliseconds. Such mysterious flashes are called fast radio bursts. They seem to be coming from billions of light-years away. Not so long ago, researchers were lucky enough to capture a repeating radio burst that flashed 6 times in a row. Who knows? It might help us crack the puzzle of these signals. But hold on, it's just the first mystery on our list. If nuclear pasta does exist, it's the strongest material in the entire universe. Formed from the leftovers of extinguished stars, this substance is squeezed into spaghetti-like tangles of material. It can break, but only after you apply 10 billion times the pressure needed to shatter steel. That single, high-energy neutrino that hit Earth in 2017 wasn't extraordinary on its own. Scientists observe such neutrinos at least once a month. But it was the first one to arrive, carrying so much information about its origin that astronomers could actually point their telescopes in the direction it had come from. They found out that the neutrino had been flung at our planet around 4 billion years ago by a flaring blazar, a supermassive black hole at the center of a galaxy. Saturn's moon Hyperion is one of the most bizarre-looking moons in the solar system, but its appearance isn't the strangest thing about it. This pumice stone-like rock, pockmarked with countless craters, is also charged with static electricity which is flowing out into space. Lost in space and drifting through galaxies, rogue planets were once flung away from their parent stars. But one of them, 200 light-years away from Earth, is different from the rest. It's a planet-sized object with a magnetic field 200 times stronger than that of Jupiter. This field is so powerful that it generates flashing auroras illuminating the planet's atmosphere. When a team of astronomers at Louisiana State University first spotted this star, they were totally baffled. The object, nicknamed Tabby's star, dipped in brightness at irregular intervals and for odd periods of time. Sometimes the difference in brightness reached 22%. Could it be due to the activity of some alien megastructure? Unlikely. The main theory claims that the star is surrounded by an abnormal ring of dust, which causes the darkening. DJI-SAT-1 galaxy is as big as the Milky Way, but it's nearly invisible because its stars are spread out incredibly thinly. But what makes the galaxy so unique is that it's sitting all alone. Unlike other galaxies of this kind, which are usually found in clusters. It can mean that DJI-SAT-1 was formed in a different era, probably a mere 1 billion years after the Big Bang. If it's true, the galaxy is a real living fossil. Massive objects curve light so much that it can distort the images of objects behind them. When astronomers used the Hubble Space Telescope to detect a quasar from the early universe, they used their discovery to calculate the expansion rate of the universe. Strangely, they discovered that, currently, it was much faster than it used to be. That finding contradicted other measurements. We still don't know if our theories are wrong or if something bizarre is going on in our universe. Neutron stars are ultra-dense collapsed cores of giant stars. They usually emit X-rays or radio waves. But in 2018, astronomers discovered a weird stream of infrared light. It seemed to be coming from a neutron star 800 light-years away from our planet. This signal was probably generated by a disk of dust surrounding the star. But this theory hasn't been proven yet. Haumea, a dwarf planet orbiting in the Kuiper Belt, has a bizarre, elongated shape and 2 moons. The day on this planet lasts 4 hours, making it the fastest spinning big object in our solar system. But the most enigmatic thing about Haumea is that the planet has a thin 40-mile wide ring circling it. Dark matter is believed to make up 85% of the universe, and researchers used to be sure it was everywhere. But in March 2018, a team of scientists discovered a peculiar galaxy that seemed to contain little to no dark matter. Later, though, it was proven that this space oddity did, in fact, contain dark matter. Moons orbiting other moons might exist, or they might not. Astronomers haven't agreed on this yet. Planets orbit stars, moons orbit planets, then why can't there be moons, also known as submoons, moonets, and muons? Researchers claim that moons could exist. But the host moon has to be massive enough, the moon small enough, and there must be a wide gulf between these moons and the host planet.
Right now, 4 tiny, Earth-like planets are chilling around one of the closest star systems to us. We're talking second closest. These little rocky worlds are each about 20 to 30% the mass of Earth. So not quite Earth 2.0, but still pretty solid. Will one of them become our new home one day? Well, all of them are pretty close, so future humans might actually visit them someday. Not like next year or anything, but we could potentially send missions there. Don't expect any extraterrestrial neighbors, though. Those planets probably aren't home to life, or at least not anything we'd recognize. Let's take a look at them. The planets are called Barnard B, C, D, and E. How creative, huh? The innermost has a mass of 26% of Earth. The second one is a bit bigger, with a mass of 30% of Earth. The third one has 4% more mass than the previous. And the outermost is... no, it's not the biggest. Actually, it's just a baby, with a mass of 19% of Earth. All the planets are likely rocky, like the inner planets of our solar system. They orbit their star very closely. That's why they only need a few days, under a week, to make a full circle. Now, what about that star these little guys are circling? It's called Barnard star. Astronomers have always had a hunch there might be at least one planet orbiting it. First off, this star is super close, in cosmic terms of course. Only the Alpha Centauri trio is closer to us. Barnard star is just under 6 light-years away, which is basically next door. At the same time, it's not like our Sun. Barnard star is a red dwarf, the most common kind of star out there. It's got only about 1/6 the mass of the Sun. But red dwarfs are a goldmine for learning about planets outside our solar system. And studying Barnard star can help scientists figure out what planets around single stars, like our Sun or this red dwarf, are like. Or what kind of environments red dwarf planets might have. And most importantly, we might finally find the answer to this super important question. Could any of these places actually support life? For the longest time, scientists thought there might be a big Jupiter-like gas giant hanging out near Barnard star. All because the star has a little wobble. It looks as if it shifts towards and away from Earth over time, so something might be tugging on it. Interestingly, it wasn't a giant planet doing the pulling. According to a study from March 2025, it's actually 4 smaller rocky planets, each about 4 times the mass of Mercury. One day, they ganged up and started tugging on the star together. These planets are incredibly close to their star, so close that they can whip around it in just a few days. Sadly, because of that, they might be way too hot for anything like life. Besides, since these 4 seem to explain all the star's movement, the researchers think there's probably nothing else orbiting the habitable zone. So, there's no Earth 2.0 orbiting around Barnard star. Still, it's an awesome find, especially since this star is basically our cosmic neighbor. Plus, the system might not stay off limits forever. With nuclear fusion engines or light sails, futuristic propulsion systems that could make the trip way faster. We might probably go there one day. And then we'll finally figure out if these worlds are really lifeless and maybe even colonize them. Now, let's see how scientists found the star's hidden planets. Normally, astronomers spot exoplanets when they catch them crossing in front of their stars and blocking some light. But Barnard star is tricky because in our view, it's like we're looking from above the system, so its planets don't block the light in the usual way. That's why they call it the Great White Whale of planet hunting. To get around this, researchers used a super sensitive instrument called Maroon X attached to the Gemini North telescope on Hawaii's Mauna Kea volcano. Over 112 nights, spread out across 3 years, the telescope picked up tiny changes in the star's movement. These shifts let scientists figure out how many planets must be tugging on the star, as well as estimate their sizes. At first, they found 3 planets. But then they used another device, deliciously called Espresso, and located at the Very Large Telescope in Chile. And only after a shot of this Espresso did they find a 4th planet. By combining the data from both instruments, they were able to more or less confidently say their findings were solid, not just random glitches in the data. Even though red dwarfs like Barnard star are the most common type of star in the universe, most are way too far for us to see planets around them easily. These new findings suggest that small rocky planets could be pretty common around these stars, and that's huge for future discoveries. Now, finding new exoplanets is cool and all, but it might be even more exciting to dwell on their birth and evolution. And a recent study has made the sweetest discovery ever. Newly born exoplanets might actually look like Smarties, that popular British candy, rather than spheres. We've always kinda assumed that baby planets are born ball-shaped, but they might be oblate spheroids instead. A team of scientists from the University of Central Lancashire in England used computer simulations to build a model of the formation of planets in dense gas disks surrounding young stars. After that, they compared these models with actual observations and noticed that the young planets took pretty unusual shapes. The thing is that even though almost 6,000 exoplanets have been discovered so far, astronomers still don't have a clear understanding of the sequence of events marking their birth and early evolution. But this new research might finally shed light on this process. So, the astronomers examined the formation mechanisms of gas giant planets like Jupiter and came to the conclusion that planets built up from their centers. After that, the researchers focused on the initial shapes of such planets. They were also interested in how they could encourage the growth of these planetary seeds. How could they turn into such massive planets, some of them bigger than our solar system's largest giants? According to the standard theory of the formation of planets, such growth happens gradually and smoothly. First, dust particles start to stick together, turning into larger and larger objects. This process lasts for a very long time and is known as core accretion. It's the model of planet formation scientists favor. There's another theory, according to which planets' birth might happen over shorter periods of time. This data involves a protoplanetary disk, a disk of gas which makes up 99% of its mass, and dust, around 1%. This disk orbits a newly formed star, and hypothetically, planets might form from this cloud. Protoplanetary disks are likely to be common byproducts of star formation. They might range in mass from 0.001 to 0.3 solar masses. Inside such disks, matter slowly moves inward, and dust particles grow bigger, to the size of pebbles. At one point, after 2 to 3 million years, a giant rotating protoplanetary disk breaks into pieces, and that's how baby planets are born. This theory is known as the disk instability model. As for the model built by the team, it seems to support this second, less favored theory, rapid planet formation through disk instability. All because this theory explains how large planets can form relatively quickly at pretty large distances from their host stars. As for the weird flattened shape of these newly formed planets, it might be due to the material falling onto them. Most likely, it goes mainly to the poles of new planets. One of the main conclusions of the research is that the appearance of young exoplanets, as we see them from Earth, may vary depending on how they're angled. If Earth is directed face on to an exoplanet, it will seem that the latter has a traditional spherical shape. But if seen on edge, a baby exoplanet will look like a real Smartie. The team is going to continue to investigate the formation of planets with the help of an improved computer model. They believe they can find out the role the environment around a young planet plays in affecting its shape and formation.
In February 2025, scientists discovered something shocking about our planet's insides. We've long thought that Earth's inner core is a solid and stable sphere. But the truth may be quite different and a bit alarming. The recent study suggests that the surface of the core might be undergoing structural transformations right at this moment. Researchers from the University of Southern California have analyzed decades of seismic data and discovered that the surface of the inner core appears to deform under the influence of the outer core. We've observed such changes for the first time, but they're likely to explain some peculiarities in the rotation of the inner core. They could even be influencing the length of days on Earth. Now, the inner core of our planet, located about 3,100 miles below the surface, is traditionally described as a solid ball of iron and nickel. However, new data
shows that its outer layer may be more malleable than expected. This discovery is based on the analysis of seismic waves from repeated earthquakes near the South Sandwich Islands. The researchers used enhanced resolution techniques to study these seismic signals. They observed anomalies in the waves and made an unexpected conclusion. There must be deformations on the surface of the inner core, and they could be caused by turbulent interactions with the molten outer core. Now, this outer core, composed of liquid iron and nickel, has a highly important role. It helps generate Earth's magnetic field. Before, we really didn't understand its impact on the inner core. But now, the new study shows that the turbulent movements of the outer core could disrupt the surface of the inner core, and that could cause changes in its shape. These disturbances might also explain the gradual slowdown in the rotation of the inner core. Scientists have been observing it since 2010. On the surface, we really don't notice these changes, but they could influence Earth's overall rotation and length of days. The study can help us understand better what's happening deep inside our planet, how the inner and outer core interact, and how that affects Earth's magnetic field and movement. Obviously, direct observation of Earth's core is impossible. That's why scientists use indirect methods, like analysis of seismic waves. It also allows us to deduce the structure and composition of the core. As these waves pass through different layers, they get deflected or stopped, and this can provide us with clues about the nature of the materials they encounter. There are also laboratory experiments. Researchers reproduce the extreme pressures and temperatures of the core and study the behavior of iron-nickel alloys. They use sophisticated instruments, such as diamond anvil cells, and they allow exploration of these extreme conditions. Then there are studies of meteorites. The thing is, some of them come from asteroids with a metallic core like Earth's. Their chemical composition sometimes provides clues about the elements present in Earth's depths. Scientists can also create numerical models. By combining seismic, experimental, and geochemical data, they simulate the internal dynamics of our core. But what would happen if Earth's core suddenly stopped spinning altogether? Well, it's unclear, but we can make assumptions. If it was just the solid inner core that stopped, the answer would be, not much. Even if it didn't just slow down its movements, which is happening right now, but stopped altogether, the main impact would be on the speed of Earth's rotation. Our days would get longer. Over time, it could weaken the planet's magnetic field, which would be bad news, but not as catastrophic as what would happen if the outer core stopped spinning. That's when things would get seriously bad. Without the rotation of the outer core, Earth would lose its magnetic field, and the loss of this protective shield would set off a catastrophic chain reaction. First off, tectonic plates would start colliding in chaotic ways. Imagine being on a bus when the driver suddenly slams on the brakes and you go flying into other passengers or on the floor. The planet would experience something similar, but with tectonic plates. Ew. These violent collisions would cause massive earthquakes along plate boundaries worldwide, shaking buildings, bridges, and roads. Water systems, electricity, and phone lines would be destroyed in the chaos. But this would only be the start. Without the magnetic field, cosmic radiation would start hitting Earth's surface. These high-energy particles from the Sun would interact with the oxygen and nitrogen in our atmosphere, damaging the ozone layer. This would allow even more radiation to reach Earth's surface, causing even more damage. Electronics would fail, power grids would collapse, and communication systems would go dark. But the effects wouldn't be limited to just humans. All forms of life would be at risk. Many animals, like migratory birds and turtles, rely on Earth's magnetic field for navigation. With it gone, they would be completely lost. Birds would lose their sense of direction, and turtles wouldn't be able to find the beaches where they need to lay their eggs. Luckily, we don't need to worry about this apocalyptic scenario anytime soon. The outer core of Earth is very unlikely to stop spinning in our lifetime or ever. So for now, we're safe. But to truly understand Earth, you need to go 4,000 miles beneath our feet. Earth has four main layers, from the very center to the surface: the inner core, outer core, mantle, and crust. Now, except for the crust, no one has ever explored these deeper layers in person. The deepest humans have drilled is just over 7.5 miles, and that took 20 years to achieve. At the very center of Earth is the inner core, a solid metal ball about 758 miles in radius, which is about 3/4 the size of the Moon. It sits about 4,000 to 3,200 miles below the surface. Made mostly of iron and nickel, the inner core is incredibly dense. It spins a bit more slowly than the rest of Earth and is intensely hot, reaching temperatures of 9,800 degrees Fahrenheit. It's like the surface of the Sun. The pressure there is staggering, over 3 million times greater than the pressure we feel on the surface. Some research even suggests that there might be an even smaller, denser core inside the inner core, thought to be made mostly of iron. The outer core is also made of iron and nickel, but in liquid form. It sits about 3,200 to 1,800 miles beneath the surface. The heat here comes mostly from the radioactive decay of elements, like uranium and thorium, causing the liquid to churn in massive, turbulent currents. This motion creates electrical currents, which generate Earth's magnetic field. Interestingly, Earth's magnetic field reverses about every 200 to 300,000 years, and scientists are still trying to figure out exactly why it happens. The mantle is Earth's thickest layer, stretching almost 1,800 miles deep. It starts just around 19 miles beneath the surface. Made of iron, magnesium, and silicon, it's dense, hot, and semi-solid. To imagine it better, think about caramel candy. Like the outer core, the mantle also circulates, but it moves much more slowly. Closer to the upper edge of the mantle, between 62 to 124 miles underground, the heat is so intense that it melts rock. This creates a partially melted layer of rock called the asthenosphere. Geologists think that this soft, hot, and slippery layer is what allows Earth's tectonic plates to move and slide. Some of the diamonds we find on Earth come from the mantle. Most of these diamonds form at depths above 124 miles. But rarer, super-deep diamonds may form as deep as 435 miles. These diamonds are brought to the surface by a certain kind of volcanic rock called kimberlite. The outermost part of the mantle is cooler and more rigid, behaving more like the crust above it. Together, this uppermost part of the mantle and the crust are called the lithosphere. As for the crust itself, it's the outermost layer of Earth. It's about 25 miles deep and makes up only 1% of the planet's mass. And yet, it holds all known life in the universe. Now, I don't want to freak you out, but something bizarre has erupted in the depths of space. It was an explosion brighter than billions of suns. But the real mystery is that it doesn't match anything astronomers have ever seen. Usually, cosmic events like this follow familiar patterns, but not this one. It's a cosmic anomaly. This strange cosmic explosion has left astronomers totally baffled. It could be a super rare event where everything lines up just right, or it could be something completely new, never seen before. This event was first detected by an X-ray space telescope called the Einstein probe on April 8, 2024. It first appeared to be a regular gamma-ray burst. Those typically give off incredibly bright X-rays. But could the answer really be so simple? Something didn't add up. Now, gamma-ray bursts are the most powerful explosions in the universe, and they can happen in unusual ways. Long-duration gamma-ray bursts are caused by the demise of massive stars that spin incredibly quickly. When these stars run out of fuel, their cores collapse under gravity, forming an extremely dense object, like a black hole. At the same time, the outer layers of the star are blown away in a massive explosion called a supernova. Gamma-ray bursts are followed by jets. Those are twin beams of material shooting out from opposite sides of the collapsing object. They're super fast, moving at nearly the speed of light. These jets appear brighter if they're pointed directly at us. It's like how a flashlight beam is brightest when it's aimed straight at you rather than at an angle. Now back to our unusual cosmic explosion. Remember me telling you something wasn't adding up? Hey, it was just 45 seconds ago. Well, the problem was that when multiple telescopes observed this event in different wavelengths – ultraviolet, optical, near-infrared, radio, X-rays, gamma rays, you name it – it didn't match any known type of event. The most likely explanation, according to current research, is that this explosion is the result of a white dwarf star being torn apart by a medium-sized black hole. And still, it's not so simple. Now, black holes are areas in space where gravity is so strong that nothing, not even light, can escape. That's why they're called black holes. It's believed that stars with at least 3 times the mass of our Sun can collapse under their own gravity once they run out of their stellar fuel. When a star has so much mass packed into such a small space, its gravity becomes so powerful that it forces everything, including atoms, to squish together. This intense density leads to the formation of a black hole. So, when a white dwarf star is torn apart by a medium-sized black hole, it results in a high-speed jet of material that can be aimed directly at Earth. So, could this space disaster be the reason behind our mysterious event? Unfortunately, even though it ticks some boxes for several types of phenomena, including the one involving a white dwarf, it still doesn't fit all the criteria for any of them. The event's short duration and high luminosity are hard to explain using any scenarios we can produce. So, does it mean we have come across something completely new? The universe is full of energetic flashes caused by outbursts from stars and black holes, supernova explosions, stars being eaten by black holes, and other cosmic events. Astronomers usually figure out what these events are by analyzing their duration, frequency, source, and the specific combination of wavelengths they emit. Here, I just have to say a few words about the instrument that discovered the space anomaly. The Einstein probe is an X-ray space telescope project led by the Chinese Academy of Science in collaboration with the European Space Agency and the Max Planck Institute for Extraterrestrial Physics. That's a mouthful. This project is all about studying high-energy space events over time. Its main goal is to find inactive black holes and figure out how matter falls into them by spotting X-ray flares produced by these sudden space events. The Einstein probe also hopes to catch the electromagnetic signals from events that cause gravitational waves, like when neutron stars merge. It also keeps an eye on the whole sky to spot all kinds of space explosions and track already known changing X-ray sources. After the Einstein probe detected that ultra-bright space flash, the event was also observed by a few other ground-based and space telescopes, including the Nuclear Spectroscopic Telescope Array, SWIFT, Gemini, Keck, Dark Energy Camera, Very Large Array, Australia Telescope Compact Array, and Neutron Star Interior Composition Explorer. That's a bigger mouthful. Using all this data, astronomers pieced together the event's characteristics, but it didn't make the case any clearer. Quite the opposite. It just deepened the mystery. This event flared up in soft X-rays for the first 10 seconds, then plateaued at a steady glow for about 4 days before fading quickly within another day. This is much longer than typical gamma-ray bursts, which usually last from a few milliseconds to several hours. But it was still not long enough to fit into other known categories. The event's brightness in X-rays was also unusual. It was too bright for some types of phenomenon, but not bright enough for others. The most puzzling part is that the Very Large Array didn't detect any radio emission from the source when it was observed 11 days, 158 days, and 258 days after the initial flare. And normally, when something this bright in X-rays lasts for this long, it's usually associated with a luminous radio counterpart. But in this case, no radio signals were detected, which is very strange and adds to the mystery. Astronomers didn't give up and considered several other possibilities, like fast blue optical transients. Those are a new class of explosions that release huge amounts of energy and blast matter into space at incredibly high speeds. These bursts are so powerful that one F-bot can be at least 10 times more powerful than a regular supernova. Fast blue optical transients do look like supernova explosions, but they are much faster. They flare up and fade away much more quickly than regular supernova. They're also much hotter, which makes the light seem bluer compared to other supernova. Since these explosions happen so quickly, it's tough to figure out what causes them. In January 2019, astronomers narrowed it down to two causes: a black hole consuming a white dwarf star, or a rare kind of supernova that leads to the formation of a neutron star or a black hole. Now, another explanation for our mysterious space explosion, and astronomers think it's the most likely one, is a tidal disruption event. It happens when a black hole swallows a star, causing a flash of light. When a star gets too close to a supermassive black hole, it doesn't get off easily. No, the black hole's powerful tidal forces tear the star apart, breaking it into pieces and pulling it toward the black hole. Its remains turn into a stream of debris that falls toward the black hole's accretion disk. However, before the debris settles into the disk, it overshoots the black hole in an elliptical path, only to be pulled back in. At one point in this path, the debris collides violently with other parts of the star being pulled in, and that's when we start to see the first bursts of emissions. In some rare cases, tidal disruption events create huge jets of material that shoot out from the black hole's poles. If these jets happen to point directly at Earth, we can see the signature of the event. It often looks like an intermediate mass black hole eating a white dwarf star. However, there should still be some radio emissions coming from the jet of a tidal disruption event. The reason none have been detected yet might be that the event was likely observed too early. Previous studies suggest that it can take hundreds or even thousands of days for the jet material to slow down enough to start sending out radio signals. If future observations pick up radio emissions, it could help solve the mystery. But if there are no signals, it might mean it's a very unusual gamma ray burst or something completely new that we haven't seen before.